Good morning, friends. Here we go. This is problem solving session on moving charges and magnetism. Moving charges and magnetism physics. So here today we'll going to solve some problems on solenoid and cyclotron related problems related problems for JE, NEET and your board examinations. Okay, so that's what we are going to see. So let's see the problem number 1. So problem number 1 goes like this. So to start with, we will do a problem on solenoid. So the first problem goes like this. A solenoid of length of length 50 centimeter having 100 turns carries a current of 2.5 amps. Find the magnetic field. Find the magnetic field in the interior of solenoid. In the interior of solenoid, and the path 2 at the end of solenoid. So this is a very simple problem. So this is at the basic level. The given the current I is 2.5 amps, and we have to calculate the value of n, which is number of turns per unit length, n by L. So n is the L is 50 centimeters, so it is 0.5 meter, and the number of turns is 100. They have given, that is n. So 100 by 0.5, that is 200 meter inverse. So number of turns per unit length is having a units of meter inverse. And now we have the calculation, the first part, that's the interior of the solenoid, that is mu naught Ni. So this is the calculation, very simple. So mu naught Ni, I is the current. So let's plug in the things. Mu naught value is 4 pi into 10 to the power of minus 7. Mu naught value is 4 pi into 10 to the power of minus 7. So this value will substitute into n is 200 into I is 2.5. So that happens to be the value, what we get is 6.28 into 10 to the power of minus 4 Tesla. That's the answer for you. At the end of solenoid, be at the ends is B interior divided by 2. So this one we can remember, that is mu naught Ni whole divided by 2. So just now we calculated the value of mu naught Ni, so that will be 6.28 into 10 to the power of minus 4 Tesla whole divided by 2, that is 3.14 into 10 to the power of minus 4 Tesla, and hence the answer. So you can note it. So let's go to the second one. You can pause the video and note the answer. So let's move on to the next one. A solenoid of length 1 meter, and 3 centimeters in diameter has 5 layers of windings. Has 5 layers of windings. Has 5 layers of windings of 850 turns. Of 850 turns. Each carries a current of 5 amperes. Each carries a current of 5 amperes. What is the magnetic field? What is the magnetic field at the center of the solenoid? What is the magnetic field at the center of the solenoid? Also calculate the magnetic flux. Also calculate the magnetic flux from a cross section of the solenoid. From a cross section of solenoid. From cross section of the solenoid at the center of the solenoid. At the center of the solenoid. If you want to give a problem this try, you can give a try how to solve this problem. Want a solution, you can pause the video and give a try, and then the solution follows. So in the meantime, what you can do is you can subscribe and then hit a like to this video. And here we go. The solution goes like this, and the answer goes like this. So what are the things which are given to us? The number of turns. The number of turns is there. There are 5 layers, each of 850 turns. So 5 times 850 will come into the picture. So the value of you can find the area of cross section also. I'll tell you why it is used. The area of cross section can be done by pi r square. So that is 22/7 you can use. And r square is the diameter they have given. So diameter by 2. So that is 3 centimeters diameter. So you can use 3/2 into 10 to the power of minus 2. So that becomes meters. That's whole square per meter. That's the area. Now why the area is given is you can calculate the flux, that is phi is equal to B times A. The magnetic field times the area of cross section. This is how one can calculate the flux. Now for that the area is given. So first idea is to calculate the magnetic field, and then L value they have given it as 1 meter. So N, let us calculate, that is N by L. So that is 5 into 850 whole divided by 1 meter. So that happens to be 5 into 850 meter inverse. So as I told you, the N value will be in terms of meter inverse. Now the magnetic field of the solenoid B happens to be mu naught Ni. So the mu naught value is 4 pi into 10 to the power of minus 7, and N value is 5 into 850 meter second meter inverse, and then the I value happens to be, what's the value of I? That's 5 amps. So that's 5 amps will substitute. So the answer works out to be 2.671. So that's 2.671 into 10 to the power of minus 2 Tesla. When you work out, this will be the answer what you get. Magnetic flux is 5B is B times A. So the B value, that is 2.671 into 10 to the power of minus 2 Tesla times you have the area is 22 by 7 into 3 by 2 into 10 to the power of minus 2 whole square is what you get. This value works out to be about 1.89 into 10 power minus 5, 89 into 10 to the power of minus 5 Tesla into meter square. The Tesla into meter square is known as Weber. So that is 1.89 into 10 to the power of minus 5 Weber. And now you have to remember this one, 1 Weber per meter square, that is 1 Tesla. Okay, so this conversion factors you have to remember. Weber per meter square is Tesla. Weber per meter square is Tesla. So I'll write again, 1 Tesla meter square. That's called Weber. That's a unit of the magnetic flux. So here we go. So that's the answer. You can pause the video and you can note, and please do like and subscribe. Thank you all. And then let's move on to the next one. The third question. There we go. The next one. An electron has an energy of an electron has an energy of 2000 eV 2000 eV describes a circular path describes a circular path describes a circular path in magnetic field in a magnetic field in a magnetic field of flux density of flux density 0.2 Tesla. The flux density is nothing but the magnetic field. What's the radius of the path? So what is the radius of the path? The radius of the path. Okay, let's see this question. The energy is 2000 eV is the thing that they have given in electron volts. So the energy is kinetic energy. So that is 2000 electron volts. The electron volts have to be converted into joules. So one can divide This one had to be multiplied with 1.6 into 10 to the power of minus 19 to get joules. So this value about works out to be 3.2 into 10 power minus 16 joules. That will be the value when you convert into joules. So 1 electron volt, the factor here 1 electron volt is 1.6 into 10 to the power of minus 19 joules. So note it up to here. You can pass the video and note. Next part is that. So we calculated the energy, and if you know the kinetic energy, you know that it's half mv square, and the value of V we have given. It's given that it's 0.2 Tesla. 0.2 Tesla. That's the value of V, which is given, and the we got to find the value of R. R is equal to, you know that it's mv by bq. So that's how one can calculate the radius of the path described by the charged particle when it is subjected to the magnetic field. So here half mv square, from this you can calculate the velocity as square root of 2 eke divided by m, and then this v will substitute over here. So R is equal to m by dq, and then instead of v I can substitute this one here, so that becomes square root of 2 eke divided by m. So that's for the velocity. This m cancels out to get a root m over here, so you get square root of 2m eke whole divided by bq. This is what you get. So the R value happens to be square root of 2 into the electron. So the electron mass is 9.1 into 10 to the power of minus 31 kg. So given what's the electron is, that the kinetic energy of the electron is what we have calculated in joules, that is 3.2 into 10 to the power of minus 16 joules whole divided by B is 0.2 Tesla, and again the charge of the electron, that is 1.6 into 10 to the power of minus 19 coulombs. So that gives the radius of the circular path, that is 7.5. When you work out, what you get is 7.5 into 10 to the power of minus 4 meters. So this will be the answer what you are going to get. So take a calculator and then give the calculations. Let's move on to the next problem. The next problem. So that will be, I think it's 1, 2, 3. Then this will be the fourth one. The fourth one goes like this: a cyclotron. Cyclotron, when being used, when being used to accelerate positive ions, to accelerate positive ions, the mass of the positive ions is about 6.7 into 6.7 into 10 to the power of minus 27 kg. This is the mass of the positive ion, and the charge on the positive ion, the charge on the positive ion is Q. They have given as 3.2 into 10 to the power of minus 19 coulombs. This is what they have given. Has a magnetic field, has a magnetic field of pi by 2 Tesla. This very nice factor they have given. They have given it as pi by 2 Tesla. What must be the value of frequency? What must be the value of frequency? What must be the value of frequency of the applied of the applied of the applied alternating electric field of the alternating electric field of the alternating electric field to be used on it, to be used in it. So that's the question. So let's read the question once again. A cyclotron, when being used to accelerate positive ions, the mass of the positive ion is given this much, 6.7 in 10 power minus 27 kg, and the charge of the positive ion is this much, has a magnetic field of pi by 2 Tesla, and what must be the value of the frequency of the applied alternating electric field to be used in it. So here we go for the answer. So the first one is, what we have to know is how to calculate the frequency in the case of cyclotron, that is dq divided by 2 pi m. So dq divided by 2 pi m. So this is the formula what we need to apply. So simply the thing is that you got to plug in the numbers, that's it, straight away. So the charge is 3.2 B. So B is pi by 2 Tesla. So let's plug in, that's pi by 2 Tesla. And again, charge is about 3.2 into 10 power minus 19 coulombs. So whole divided by, you have 2 into pi into the mass of the particle is 6.7 into 10 to the power of minus 27 kg. So this is the formula where you can apply, you can cancel the pi's, and then this cancels out to be 1.6 times. I hope so you understood. So the frequency works out to be, so when you give the calculation, it works out to be 1.2 into 1.2 into 10 to the power of 7 cycles per second, or as you can say it's, that's much will be the frequency. So it's actually cycles per second, cycles per second. This other way one can give you the answer. So you can make a note of this. So let's see another question now. Two long coaxial insulated solenoids S1 and S2, S1 and S2 of equal lengths, of equal lengths are bound or wound one over the other one over the other, one over the other, as shown in the figure, as shown in the figure. So I'll try to draw the figure over here. You can see this. It's like you have one solenoid like this, and let me draw with a different color. The other solenoid will be over this like this. So it's very tough for me to draw, but I'll try my best. So it's like one core, and again over this inside. So I'll draw with a different color. So that the inside one will be like this. So you have, I'll draw a cylinder. Over that I will give the winding so that you will understand it much better. So it's like this. Okay, this is one. The second one, the outer one is like this. This is the outer one. So hope you understood one over the other. So they are winded like this. So they are wounded closely. So the windings are very close. So it's a close wind. Now this is what they have given. And what else we have? Now what else they have given? I'm just reading the question. So a steady current I, a steady current I flows through the inner solenoid S1 through, so this we can do through the inner solenoid. So the inner one is the S1, the outer one is S2. So through the inner solenoid S1 to the other end, to the other end. So this is the A end, this is the B end, to the other end B, which is connected to, which is connected to outer solenoid S2. So after this part you can make a note. So of the things, outer solenoid S2. Through which the same current, through which the same current I flows, the same current I flows, same current I flows in opposite direction, in opposite direction. So this is what they have given. Now you can pause the video and then you can make a note of the things up to now in the same direction, in the opposite direction. So as to come out, so as to come out of the A end. So it's like current is flowing from the A end to the B end inside, and somehow the B end is connected to the outer solenoid, and the current flows like this. In the outer solenoid S2 and the S1, it's like this. This way in the S1 and this way in the case of S2. Okay. If N1 and N2, if N1 and N2 are the number of turns per unit length, number of turns per unit length, find the magnitude, find the magnitude and find the magnitude and direction and direction of the net magnetic field, find the magnitude and direction of the net magnetic field at a point at a point at a point A, at a point path A is inside on the axis. Okay, inside on the axis, and the point B is like outside for the combined system, outside for the combined system. This is what is given. So you can pause the video and then make a note of this. So let's see how do we solve the problem. So the first part is like for the, you can say for the inner solenoid, the net. So B net is like I can do like B2 minus B1, that is the net magnetic field. So that is mu naught N2I minus mu naught N1I, as simple as that. So it is mu naught I into N2 minus N1 because the currents are flowing in the opposite direction. Now the direction, the net magnetic field direction, the net magnetic field direction is from B to A. Here we have an assumption that N2, the number of turns in the second one is greater than the number of turns in the first one. With this assumption, we can tell that it is from B to A. So the next part is, this is the part A. The part B is like they ask to consider both the solenoids, both S1 and S2 as a system. For this system, outside what is the magnetic field? B outside for any kind of solenoid is 0. So this is the fundamental idea. This is for the ideal case. We'll consider the ideal case and give the answer to be 0. So the field outside the solenoid, that means if it's like the inside, this is the inner core, this is the inside solenoid, and then you have an outer core outside the solenoid. So what they're asking is that you consider these two, this entire stuff, the S2 and the S1 part as a one single system. When you consider the S2 and S1 as one single system, the funda what you can see is that they ask this space outside the space of both the solenoids. Outside space, this entire system you can consider as one single solenoid. Outside the solenoid, the field is zero. So this is for the ideal case, it's zero. So as per the question, it's zero. So thank you all. With this, we'll conclude this video. And thanks for the patience. Thanks for watching. If you like the video, please do subscribe and hit a like. Thank you all.